Once understood the main principle driving air movement inside and around buildings, we move on to the evaluation on the airflow rate due to gross ventilation and stack effect. In particular, in some cases, it may be preliminarily estimated by simplified methods. About cross ventilation, in general way, the airflow rate, V uppercase, passing through opposite openings is given by the coefficient of effectiveness, K, times the net free area of inlet opening, A, times the outdoor wind speed, V lowercase. K depends upon the direction of the wind relative to the opening and on the ratio between the areas of the two openings. It is maximum when the wind blows directly onto the opening, and it increases with the relative size of the larger opening. For opposite openings of equal area, K equals 0.6 for perpendicular wind, and it equals 0.3 for wind at 45 degrees. Changes in wind direction up to 30 degrees on either side of the normal to the window wall have little effect on the values of K. For wind directions outside these limits, the value of K may be considered to change linearly with the wind direction. According to the type of window, jalousie, sash, casement, and so on, the net free area of an opening is different, and it is obtained by multiplying the gross opening area by the window permeability. In brackets, typical values for different window types are reported. The same algorithm may be also useful to size the opening area, if explicit in function of it. Let's move on to an example. We want to size two opposite openings of equal area in a room in order to ensure an airflow rate equal to 0.8 cubic meters over second. Let's assume that outdoor wind velocity is equal to 2 meters over second and its incident angle is 45 degrees, so K is equal to 0.3. Then the needed opening area is given by the airflow rate over K times V, which results in this case 1.33 square meters. If opening areas are different, some graphs available in the scientific literature may be useful. They provide the airflow rate per square meter through the smaller opening with different wind speed. With the same data of the previous example, let's assume that the inlet net opening area is twice the outlet net area. We identify on the x-axis the proper ratio between the opening areas, that is 2. Then we intercept the 2.0 wind velocity curve. Finally, we read on the y-axis the airflow rate given by 1 square meter opening area referred to the smaller one. In this case, 0.75 cubic meters over second for each square meter. It means that if we want to ensure a total airflow rate of 0.8 cubic meters over second, we must divide it by the red value in order to obtain the smaller opening area. The bigger one, in this case the inlet opening area, will be given by the smaller net opening area times the ratio between the two. A compromise between the absence of information about air velocity and the detailed knowledge of its value in each part of the internal space is an evaluation of the average wind velocity. From it we can derive, as a first approximation, an indication of the effect of the airflow on comfort. The graph shows the relationship between the opening area over the total wall area, the ratio between inlet and outlet opening area, the internal air velocity as a percentage of external wind speed. It refers to a cross-ventilated room with two center opposite openings. For different relative location of openings, the obtained value has to be properly corrected by the factors reported in the table according to the wind direction. Moreover, louvers used for protection against direct solar gains significantly affect the average indoor airspeed and the airstream pattern. So a further coefficient has to be applied to the average indoor air velocity. Also, the presence of a veranda on the windward or leeward side of the room influences the air, and an additional correction factor has to be considered. Fly screens or mosquito nets are, in many cases, an absolute necessity, but they substantially reduce the airflow. A cotton net can give a reduction of 70% in air velocity. A smooth nylon net is better, with a reduction factor of about 40% of the airflow rate and about 35% of the average indoor airspeed, as shown in the graph. Here it can be noted that the reduction of the latter increases, but not dramatically, with the outdoor wind speed, and it is also affected by the wind's angle of incidence. Heated by internal loads, air entering a building that is not air-conditioned tends to rise. This because it warms up and its density, and therefore its weight, is lower than that of the outside air. If there is an opening at the top, the warm air escapes through it and is replaced by the outer, colder and heavy air, which enters from the bottom. In this way, the stack effect occurs. In the absence of wind, if internal resistance to flow is not significant, the airflow rate V crossing two equal-size openings at different heights through the stack effect depends on the difference between the internal average temperature Ti and the external one To, on the height difference H between the two openings, and on their net equal area A multiplied by a constant factor equal to 2.88. If the inlet and outlet area are not equal, the airflow is first determined using the smallest of the two areas, and then, according to the ratio between them, the percentage of the flow increase can be provided by a graph. Where appropriate, the same correction factors for louvers and fly screens as for cross ventilation should be applied. Since the airflow increases with the stack height and the temperature difference, the height difference H between the two openings should be increased as much as possible, as should their size. Because of the explained law which drives the stack effect, the related flow rate may be enhanced by increasing the temperature difference between inside and outside. To reach this goal, a solar chimney may be provided, exploiting in this way solar energy to heat the rising airflow. The actual airflow in a building results from the combined action of stack effect and wind forces. The two effects may either reinforce or oppose each other, depending on the direction of the wind and whether the internal or external temperatures is higher. When acting simultaneously, the resulting airflow rate through the building can be calculated as the square root of the sum of the two squared airflow rates. In conclusion, stack effect and cross ventilation may widely affect airflow through buildings. Hence, designers should preliminarily evaluate their magnitude also by using the presented methods.